So dear students, welcome to another lecture of digital control systems. In this lecture, we will discuss about the region of convergence in Z transform. Now, as we all know that Z transform is nothing but it is the counterpart of Laplace transform for discrete time signals. So the purpose which a Laplace transform serves for continuous time systems, the same purpose is served by discrete Z transform for discrete time signals. So in our previous lecture, we have already covered this point, and we have understood that how this Z transform is used for the analysis of discrete time systems. Actually, this Z transform is basically a generalized form of Fourier transform. So we have discrete time Fourier transform, which is expressed by this formula, right? And we have Z transform of a given discrete time system or discrete time sequence, which is given by this formula. So if you compare these two formulas, so you will get that if we replace Z is equal to e raised to the power j omega, we will get the Fourier discrete time Fourier transform of the same sequence. So we can say that we have Z in Z transform and this in discrete time Fourier transform, right? Now, the Fourier transform does not exist for all the signals. Similarly, we will not have the Z transform of all the sequences. In this equation, this Z represents a complex variable. Like in Laplace transform, we have S, which is the Laplace operator. So this is the Laplace operator. Similarly, in Z transform, we have a Z operator, or here we have S operator, Laplace operator. Similarly, we have Z operator in Z transform. So when we substitute Z equal to A j omega in this particular equation, we will get the Z transforms. We will uh, get the discrete time Fourier transform or DTFT equivalent of Z transform. So this has been covered in previous lectures. Now, as far as Z plane is concerned or DTFT is concerned, Z transform is basically expressed in terms of Z, which is nothing but the complex variable, right? So we generally describe this complex variable as Z plane. And if we plot Z is equal to Ej omega from omega is equal to 0 to 2 pi, we will get a circle whose radius is equal to 1, and hence we call this as unit circle, right? So this is a unit circle. This unit circle plays a very important role for the analysis of discrete time systems. Why we call it as unit circle? Because its radius is 1. And how did we get this unit circle? When we consider this equation, we put omega is equal to 0 to 2 pi. So when we plot this value, this equation, we will get a circle and its radius will be 1. Now, this discrete time Fourier transform, it has a limitation that it will not always converge. Now, when we say converge, we actually mean to say to have a finite solution, finite answer, right? So this does not have a finite answer because it is an infinite sum. You can see the limits here. So generally we do not have the finite solution of the given sequence. And the condition is that this xn is not the, if it is not summable actually, right? For example, we have xn is equal to a raised to the power n un. So this is, let us say, some sequence. So if you put the value of a greater than 1 for this particular, its discrete time Fourier transform will not exist because it will not converge. Now, if we have this z, which is the complex variable, if we write it as r e raised to the power j omega, where r is the radius of the circle. So when we put the circle which is formed by putting omega is equal to 0 to 2 pi, right? Now the z transform of this, if we replace z with rj omega in the equation, which equation? We have xz is equal to summation n is equal to minus infinite to infinite xn e raised to the power minus, sorry, z raised to the power minus n. The given infinite summation will have the finite answer. Now, this is what RoC is, region of convergence. Now, when we talk about region of convergence, it is that region in Z plane. So, first of all, we need to understand this thing. So, we have a Z plane. So, this Z plane is obtained by putting Z is equal to e raised to the power j omega. So, we can compare this with the given Z is equal to r e raised to the power j omega. So, if you compare these two, so r is equal to 1. That means we have a unit circle, right, which is in Z plane. So, this Z plane will have certain values of Z. For these values of z, the given z transform of any sequence xk or xn should or must converge. Now, when we say convergence, when we say that the given z transform should converge, we actually mean to say that its in this infinite summation should be less than infinity. Its answer should not be infinite, it should be less than infinity. That means it must have a finite answer, it must have a finite solution, right? It could be 0, it could be 1, 2, anything, but it is not infinity, right? And this will only be possible when the given sequence into this given sequence xk, if it is absolutely summable, right? So we can say that we have this region. So that, for example, this is a Z plane here and we have some circles here. So every circle will have some radius R. Let us say this is R1, this is R2, this is R3, for example. So it may have different values of R. Okay, so in this region, as you can see this shaded region here, this shaded region will have the values of z, for which let us say some z transform of any given sequence will have some finite answer. So that is why, to summarize, we can say that a set of values of z, the set of values of z which are available in the z plane, and for these values of z, the given z transform of any given sequence xk will converge. It will not diverge, it will converge. So this r, if you go behind this r, basically this r in this equation will represent the radius of the circle. So we may have different values of r. Okay, so and we will choose the value of r in such a way that the answer of a given z transform should be finite. Generally, this r is equal to 1, so that we have a unit circle. and we do the analysis on the basis of unit circle, right? Either our values of z are lying within the unit circle or lying outside the unit circle, or there is a ring basically, right? So we may have different type of regions where we have the values of z for which the given z transform converges, right? So in this example it would be more clear to us. Like in this first figure, if you see, this is the region of convergence of a sequence in which if the values of z are less than a. So what is a here? A could be some point on this axis, it could be here also, it could be here also, it could be here also. That means the value of z, the value of a would be, like you can say, the radius or the point on the outside the unit circle or on the unit circle, right? So we can say that if the values of z are less than this a, so that means this shaded region, if you see, so this shaded region is on the z plane, right? This is z plane, this is real, this is imaginary, right, axis. Now the values of z in this region are less than a. So this particular ROC belongs to a sequence which will converge for all the values of z which are less than some value a, some number a, right? Similarly, in this particular diagram, you can see that this is the region of convergence. This is the real axis, this is the imaginary axis, right? So this is the region of convergence of a sequence which will converge for all the values of z which are outside this circle, outside the circle. So that means it will not converge for any value of z which lies here in this particular circle. It will diverge for these values, right? Then we have a ring based ridge ROC. This is ring based ROC. In this, we can say that the values of z will lie between some number b and some number a. Okay, so the ROC means this particular sequence to which this region of convergence belong will converge for the values of z which exist between b and a. So this will be possible for some two-sided sequence. We will see it with an example, right? And here this particular sequence which is which has some ROC which is represented by this diagram. So this particular sequence will converge for all values of z. It will have a finite answer, right, for all values of z. So here we have taken four cases. Either the given sequence converges for the values of z which lie in the circle, or the given sequence converges for the values of z which lie outside the circle, or there would be a ring basically. So the values of z which lie in a particular ring, so there are two circles you can see here. This is r1, for example, this is some r2. Okay, so this is r2 minus r1, right? So for this particular region and the values which are available in this region, the values of z which are available in this region, for these values the given sequence will converge, and this will converge for all the values of z. Now this region of convergence has certain properties. Like first is the region of convergence of z transform is indicated with circle in z plane. So you can see here, okay, so we will have some circles. So Okay, so here also in this particular diagram here, it has circles, infinite circles here, right? It has infinite circles. So actually mean to say is that for all the values of z, for all the values of z which are available on the z plane, this particular sequence will converge. So the first property is that we indicate the region of convergence in a circular form. So every circle will have a radius, and we obtain this with the help of expression r z is equal to r e raised to the power j omega. ROC does not contain any pole. Now what does it mean? What is this? For example, we have a this transfer function xz is equal to this is, let us say, qz, and this is, let us say, pz, for example. Okay, so anything you can take, find qz or qz doesn't matter, right? Now in this the roots of this particular gives poles, right? Now the poles are obtained if we put pz is equal to 0. If pz is equal to 0, then xz is equal to infinity. So that means, and what we are saying, in region of convergence, what are we saying? We are saying that the given sequence must have a finite answer. It should converge, but here the xz has diverged, it has become infinity. So that is why we say that region of convergence will not have any pole. Okay, because poles are obtained by putting the denominator part of the transfer function of a discrete time sequence equal to 0. When we put the denominator of a given transfer function of a discrete time system equal to 0, we get the poles, we get the roots, and the roots of this will give us poles. So if it is so, then xz will become infinity. But ROC says that the z transform should converge. It is not converging here. So ROC does not contain any pole, right? Then if the given sequence is a finite causal sequence, so causal sequence is the one which contains the present and past uh, data, right? So the causal sequence depends upon the present and past data or values, right? So it is also right sided sequence, right? So in this case the region of convergence will be entire z plane except z is equal to 0. That means if we put z is equal to 0, if we put z equal to 0, if we put z is equal to 0 in this case, then xz will be infinite, right? So that means in such cases where we have a causal sequence but the finite duration is there, we will say that this will converge for all the values of z, but not for 0, not for 0. Similarly, if the given sequence is a finite duration but anti-causal means which has the future values also, right? Either future values also or only future values, right? That is anti-causal, right? So it is also known as left-sided sequence, right? So in this case the region of convergence will be entire z plane but not equal to infinity. That means if we put z is equal to infinity in the z transform of xk, then xz will be infinity, right? So it will not converge for the value of z equal to infinite. Then we have some infinite duration causal and infinite duration anti-causal sequences, right? So in this case For infinite duration causal sequence, the region of convergence is exterior to the circle with the radius z greater than a, right? That means the radius of the circle should be greater than a. For these values, the given sequence will converge. Similarly, like in this case, in this you can say here, this is uh, the this one is representing this case. If xk is infinite duration causal sequence, so this is the infinite duration causal sequence RoC. This is infinite duration anti-causal sequence RoC, right? So RoC is interior of the circle, interior. So here the RoC is interior of the circle, right? If we have finite duration two-sided sequence, then the RoC is entire Z plane but not 0 and infinity. So if the given sequence is both, here also, if we have both the values, so in this, the RoC will not be existing for Z0 and Z infinity. And for the rest of the values, it will exist. Now, we'll take the examples. Right. So the first example is xn is equal to 1, 2, 0, and 1, for example. And it is a right sided. So this is a finite causal sequence. This is a finite causal sequence, right? Because it is a finite causal sequence, so here n is equal to 4, right? So 0, 1, 2, and 3. So this is n. So there are 4 samples, 0, 1, 3, and 3 4 samples are there, right? So the z transform of this particular sequence, so the Z transform of this particular sequence can be obtained by using the same formula. So n is equal to from 0 to 3, right? 0, 1, 2, 3. Sample 1, sample 2, sample 3, and sample 4, right? So this is xn and z raised to the power minus n, right? So we will open it. So we have x0 z0 plus x1 z minus 1 plus x2 z minus 2 plus x3 z minus 3, right? Now if we put the values here, now what is x0? So x0 is 1, x1 is 2, x3 is 0, x4 is 1, right? So we will put it here 1 into, so z raised to the power 0 is 1 plus, so it is 2, 2 into z raised to the power minus 1 plus x2, 1, 2, sorry, x2 and 3, sorry, x2 and 3. So x2 is 0, so this is 0 into z raised to the power minus 2 plus x3 is 1 into z raised to the power minus 3. So this is 1 plus 2z inverse plus z raised to the power minus 3. So the xz of this sequence, this is a finite causal sequence. This is a right sided sequence, right? Now why it is right sided sequence? If you plot this n xn, right? So 0 we have 1, then this is 0, this is 1, this is 2, this is third sample, right? This is third, zeroth, first, second, third. So there are 4 samples. So at 1 we are have it equal to 2, so this is, let us say, 2. At 2 it is 0, at 3 it is again 1. So it is a right sided, right? Causal, this is a causal sequence, right? Because it depends upon the present and past inputs, past values, right? So xz is equal to 1 plus 2z inverse plus z minus 3. Now if we write, we can write it like this also, 1 plus 2 raised to 2 by z plus 1 by z cube. If z is equal to 0, then x 0 is 1 plus 2 by 0 plus 1 by 0 is equal to 1 plus infinite is equal to infinite, right? If z is equal to infinity, then x infinity is 1 plus 2 by infinity plus 1 by infinity cube is equal to 1 plus 0 is equal to 1. So this shows that the given sequence will converge for all values of z except z is equal to 0. So hence it is proved. Hence it is proved. Read the property number 3. If xk is a finite duration causal sequence or right-sided sequence, then RoC is entire z plane except z is equal to 0. So that means this particular sequence will converge for all the values of z except z is equal to 0. Right? So hence it is proved here, right? Now